Hello students, in the last video we have discussed about universal Turing machine and undecidable problems. So what does it mean? If you are given a problem P, right, undecidable problem means any property of this P is decidable or undecidable. Like, so whether a string is belongs to this problem or language, whatever it is, membership problem, membership property, whether it is decidable or undecidable. Right, and finiteness problem, whether it is decidable or another property, finiteness property is decidable or not in this. Okay, don't worry about the terminology, guys. So whether the equivalence property, whether it is decidable or undecidable under the two problems P1 and P2, those are undecidable. As I told you, if there is a Turing machine existed, that is decidable, right? If there is a no Turing machine existed, right, or if it is existed with infinite looping and which is not converted to without halting, right, or with halting cannot convert it to halting, then also it is undecidable. I gave some diagrammatical representation of these things in the last video, right? And then how to prove? For example, you know that some problem is decidable. Assume that membership problem is decidable in all the languages except recursive enumerable language. I gave the table in the last video. Right, for some problems for regular languages, CFL, CSL, RCL, this is decidable. Okay, then some problems are undecidable, like optimization in compiler design, ambiguity in context-free grammar. Okay, these are not decidable. These are undecidable problems. Okay, optimization and code optimization in compiler design, and ambiguity, right? Ambiguity in context-free grammar. To prove that these are undecidable, we have to consider some characteristics or properties, right? Then you don't know some other problem, some XYZ problem you have, right? Then you want to prove that whether it is decidable or undecidable, right? There are two ways. You can write your own algorithm to check it, but that is difficult. Then what we can do, take the properties of this problem. If some property can be reduced to the property of another problem, right? See if A is reducible to this. If this is decidable here and also decidable here. If this is undecidable here and also the property is undecidable, like that. If you have n properties, A, B, C, T, like that, we have n properties. Then if all the properties can be reduced to this property, which is decidable here, then also decidable here. If some properties can be reducible to this, which is decidable, but some properties cannot be reducible to this, or we can reduce where it is also undecidable here, then also undecidable. So this reducing to prove that something is undecidable or decidable, that we call it as a Rice theorem. Here Rice proposed a theorem to prove the decidability or undecidability. Most of the time we can say that undecidability only, right? So same concept. Let me go with that. What exactly the Rice theorem is stating, that any non-trivial property of the language recognized by the Turing machine is undecidable. Non-trivial property, right? Trivial property means it is all true. Non-trivial means some are true, some are false. Non-trivial property. So if you use a non-trivial property of the language recognized by the Turing machine, if you are proving that the property, assume that we have generated a Turing machine for some language, right? So if any non-trivial property which is pre-proved, that for example we have a property px and I've already proved that this is non-trivial property, and if this property is also satisfying this language, then I can say that this language is undecidable language. So the Rice theorem is having set of non-trivial property, and it will try to check that whether this is satisfying this or not, whether this non-trivial property is recognized by this or not. Like that, it will try to prove it. If it proves, then it is undecidable. So this Rice theorem works here. That's what I told you. Right? Then you may get it. So why you have told your reductions in the earlier case? So, but how you know that that is a non-trivial property? So that all the properties we have to reduce to some other. So if everything is reduced, that is a trivial. Some are reduced, some are not reduced, that is a non-trivial. Okay. Then how to check it? First, we have to identify the property, define a property you are interested in. But this should be a non-trivial property of the language recognized by the Turing machine. So the property what you are taking should be non-trivial. And how to check the non-triviality here, meaning that is at least one Turing machine whose language has the property P, and at least one Turing machine whose language does not have the property P. So we should verify that at least one Turing machine having that property and at least one Turing machine does not have the property. So you should identify both. If you can't identify any one, like all the Turing machines are having that property and all the Turing machines does not having that property, we can say that it is a trivial. Trivial means either all true, right, for that statement, or all false for that statement. Non-trivial means some are true, some are false. Then if you identify such property, then use the Rice theorem, stating that if non-trivial property can be recognized by a recursively enumerable language. If so, then we can say that whatever the language which is recognizing this non-trivial property is undecidable. So simply we can say that no algorithm decides whether that language is having the property or not. That's it, right? So then before going to the applications of Rice theorem, let me tell you what exactly the property here. See, infiniteness is a property of an infinite language. So the language must be defined by some descriptive device, either it can be a Turing machine or finite element or whatever it is. But the most general device we are going with the Turing machine. So generally we'll think that property is a problem about the Turing machine. I told you now, don't worry about the property problem, the words. Okay. So let LP, the property belongs to the language, is a binary set of binary Turing machine codes for TM such that the language accepted by this Turing machine is having that property like emptiness, finiteness, or whatever it is, right? So there are two trivial properties P for which a language is decidable. If you are saying that a language is decidable, it should be having the two trivial property, as I told you. Always false property, which contains no recursive enumerable language. If it is always false property, means we can't derive any Turing machine for it. And there is always true property, which contains every recursive enumerable language. Right? The always true property. So Rice theorem saying that for every other property P, if it is always false, trivial property, always true, trivial. If it is the remaining all, then the language is undecidable problem. Right? So recursive languages are closed under complementation. So we need a technique known as reduction, where an algorithm converts the instance of one problem to instance of another problem. Then we can prove it. As I told you now. So we have a problem here X and we have a problem here Y, and we have already proved that some property P is non-trivial, right, with regarding to this X. Then if you want to prove that same properties P is non-trivial, right, regarding Y, then take any other problem of X or Y, sorry, any other problem like infiniteness problem, finiteness problem. If this problem can be reduced to this P, right, as it is non-trivial here and also non-trivial here. If it is decidable here, also decidable here. If it is undecidable here, also undecidable here, right? So let me give a general example in this case, guys. For example, we have a traveling salesman problem, okay, and we have a visiting vertex problem. Traveling salesman problem starts from one place and going all the places exactly one, and you should return them. Visiting vertex, we have a graph, okay, then we have to visit every graph and we have to come back. So for example, in traveling salesman problem, infiniteness is undecidable, and I want to prove that whether infiniteness, is there any possibility of infiniteness in the visiting vertex. Then we have already proved that infiniteness is undecidable here, but we have not proved that whether infiniteness is decidable or undecidable. Then what we can do, if we could able to reduce this visiting vertex problem to the traveling salesman problem by taking every vertex as a place and the edge is a distance here, then once you can reduce this to here, then if some property is decidable here also. If some property is undecidable in traveling salesman problem, definitely undecidable in visiting vertex, because we have reduced this problem to the traveling salesman problem. Once you have reduced, everything is decidable, also decidable here. Everything is undecidable, also undecidable here. Right. So reduction, as I told you, if X is in LF, only if W is in L, where we are reducing the L to L dash. Right. So if we know that L is undecidable, then of course L complement, the reduction language cannot be decidable. That's what we have discussed. Right. The proof of Rice theorem here, we shall show that every non-trivial property P of the recursive enumerable language, the property in that language is undecidable. Of course, we have discussed this with the examples earlier. We show how to reduce the language to the production, where undecidable property to the non-trivial property. Assume that we have a machine with a string, a real reduction algorithm, and we are reducing it to another property, right? So that hypothetical algorithm phi. So if accepts, if and only if M accepts a W, right? Otherwise, halt with the accepting. So this would be an algorithm for some undecidable problem which doesn't exist. So same language here. So you are taking some property here for the machine, and we are reducing it to M dash, and there is an hypothetical algorithm for the property P. So the string will be accepts if and only if the machine accepts it. Otherwise, it will be accepted without halting. Then where we are going to apply this Rice theorem? As I told you, there are so many applications. Like if you want to prove that a language is regular or not, take a non-trivial property, and if this is satisfying here, then we can prove that it is not decidable. If it is not belongs to the regular language, then it is decidable, like that. So same, prove that contextual languages include any palindromes, whether it is empty or not. Does language accept a content more than 1,000 strings? Like wherever you want to prove that whether it is decidable or undecidable, take a property, okay? And if you could able to prove that this properties belongs to this, and of course make sure that this property is non-trivial. If this property is also recognized by this machine, then it is undecidable. If can't, decidable. Right? So in the next video, we'll discuss about post correspondence problem.